Good morning, students. Today we will see the topic determination of the motion of a particle. It's one of the topic in kinematics of particles in engineering mechanics. So I am Dr. R.A.K. Selvakumar, Senior Associate Professor in Design and Automation Research Group of School of Mechanical Engineering, Vellore Institute of Technology, Chennai. So as we recall, motion of a particle is known if position is known for all time. So typically, conditions of motion are specified by the type of acceleration experienced by the particle. So determination of velocity and position requires two successive integrations in general. So now we will consider three common classes of motion. The first one is acceleration given as a function of time, that is a is equal to f of t. The second one is acceleration given as a function of position, that is a is equal to f of x. And the third one is acceleration given as a function of velocity, a is equal to f of v. So one by one we will see. The first one is acceleration given as a function of time, a is equal to f of t. So the first term dv by dt is equal to a is equal to f of t. So that is second term we are rearranging it, dv is equal to f of t dt. So now we have given acceleration as a function of time. So this equation defines v in terms of t. So the next one is we are integrating on both sides with initial and final values. So in order to define the motion of a particle, it is necessary to specify the initial conditions of the motion. So here the value v naught of the velocity at t is equal to 0. So rather than using an arbitrary constant that is determined by the initial condition, it is often more convenient to replace the indefinite integrals with definite integrals, because definite integrals have lower limits corresponding to the initial conditions t is equal to 0 and v is equal to v naught, and upper limits corresponding to t is equal to t and v is equal to v. So this will give you the values v of t minus v of 0 is equal to integral 0 to t f of t dt. So now we will move to the next one. Dx by dt is equal to v of t. And further we can substitute dx is equal to v of t into dt. Further we can integrate on both sides with the initial and final value of x, that is x is equal to x naught to x is equal to x. So finally we will get the term x of t minus x0 is equal to integral 0 to t v of t dt. So in this way we can obtain the position coordinate x in terms of t. So the motion is completely determined. So the next one is the acceleration given as a function of position. So a is equal to f of x. So we have v is equal to dx by dt, or we can write it as dt is equal to dx by v. Next a is equal to dv by dt, or a is equal to v dv by dx, that is equal to the function of x. So now the acceleration given as a function of position, that is a is equal to f of x, this term. So next one, v is equal to dv is equal to f of x dx. Then integrating with respect to the velocity v naught to vx, integral v naught to vx v dv is equal to integral x naught to x f of x dx. So we will get 1 by 2 v of x square minus 1 by 2 v naught square is equal to integral x naught to x f of x dx. So just what is happening in the mathematical background I want to explain to you regarding acceleration given as a function of position. This last integration cannot be performed analytically, and we must resort to a numerical method of integration. Okay. The third one is acceleration given as a function of velocity, a is equal to f of v. So you can see the first term, dv by dt is equal to a, is equal to function of velocity. Then dv by f of v is equal to dt, so we are rearranging the term. And then similar to the earlier cases, we are substituting the initial and final velocity and the initial and final time. And we got the relation integral v0 to v of t dv by f of v is equal to t. And the next one, v is equal to dv by dx is equal to a. So again we are writing as a function of v, and dx is equal to v dv by f of v, and integral with initial and final position and initial and final velocity, x0 to x of t and v0 to v of t. So integral x0 to x of t dx is equal to integral v0 to v of t v dv by f of v. So finally you will get the value x of t minus x0 is equal to integral v0 to v of t v dv by f of v. So in this integration of the first equation, that is integral v0 to v of t dv by f of v is equal to t, that particular equation yields a relation between velocity and time, and the integration of the second equation, that is x of t minus x of 0 is equal to integral v0 to v of t v dv by f of v. This particular equation yields a relation between velocity and position, that is v and x. So either of these relations can be used to relate with v is equal to dx by dt to obtain the relation between x and t that characterizes the motion of the particle. Thank you. Further we will see in the next class. Thank you. Have a nice day.